Hi, welcome to rule of acquisition number 3. This is the utility fallacy, which is monkey do does not mean monkey know. This is for general audiences. Now, the following may either frighten you or help you set you free. I'm going to show you that in spite of today's technical marvels, humans actually know very little about what it is they are doing. In other words, monkey do does not mean monkey know. The key argument, the next slide demonstrates humans do not need to know much about something to put it to extensive use. And let's talk about fire. Fire was used effectively for over 20,000 years to heat, illuminate our homes, cook our food, and burn down the crops and homes of our enemies. Most of the time we did not know what fire was. We thought it was an element. Some people thought it was alive, yada, yada, yada. It's only about 200 years ago that fire was understood to be a chemical reaction. Okay, but even then, we go down the echelons. Okay, fire, we know the mechanical process. Then we understand the chemical process. But what about the physics of the atoms? How does that? We don't really. We know certain depth of what's going on, but we don't know anything deeper than that. Just because we understand it's a chemical process doesn't mean we understand how the nuclear, how the electrons and protons bring this all about. We have a vague understanding. That's part of the research in physics is to find out how the molecules work below the atomic level, at the atomic level. That is the next echelon down. We don't know that far down. Electricity, this one I love. We use electricity with great effect, and we consider ourselves to be marvels of electricity. And I had a discussion with somebody on the YouTube channel where the guy said to me, well, you obviously don't understand what an electric field is. And I have to laugh because, yes, he's absolutely right. Nobody knows what an electric field is. You know, and let me show you. This is what we know. This is Coulomb's model. I don't call it Coulomb's law. Law is a wrong description of this. All this model here is some scientist long ago, his name is Colonel Coulomb, charged two spheres, measured the distance between them, charged them to a known amount of charge, and then measured the force between them. And then he did that for a number of different charges and a number of different distances, and after a while they realized that the relationship between the force and the charge was an inverse square relationship in distance. And what they needed, they came up with this arbitrary constant of relation to make it all work. So this is empirical data where they found a mathematical model fit the data exactly. You just needed an arbitrary constant of relation. Okay, so this is really an empirical model. This is a mathematical fit of empirical data. This isn't a law. It's not handed to us by God on stone tablets. Okay, and there's a lot of problems with this. This doesn't tell us everything. This doesn't tell us how fast, if I quickly move this sphere, how quickly that effect is going to travel to the other sphere. It doesn't tell us that information. It doesn't tell us what travels across space to affect the other charge. It doesn't tell us very, very little. Okay, this is just us using mathematics to mimic what we observed in an experiment. That's it. It's nothing more. This isn't a law. It's just an empirical model of observed, but we put it to great, fantastic use. Wonderful use. But just by what I told you, there's a lot we don't know here, and that's part of ethereal mechanics, is to go and try to explain what is the thing that travels across space. Okay, how does one thing emit, and how does the other couple it? That's all information that is not here. And how fast does it travel? We don't know that from this. This is missing a lot of information. But this guy is like thinking that he knows everything by electric field just because he knows this. This is very little. This is just a tip of the iceberg, friends. But we can do fantastic things with it. Again, because we can do fantastic things doesn't mean we really know much about what it is we're using. Medicine's another example. This molecule over here is what's called salicylic acid. It comes from the bark of the willow tree. It is the primary base ingredient for a remedy called aspirin. Okay? And aspirin, they changed around the molecules and came up with acetaminophen. And then they changed the molecules and they come up with ibuprofen. They don't know what's going to happen. They just make little changes and then they do some experiments and make sure it's safe and they give people and say, what does it do? No one knew that changing it this way would create a wonderful thing called ibuprofen. Now, to show you how little we really know, this piece of paper is what you get when they prescribe for you ibuprofen. This is what you get from the pharmacist. You probably can't read it from there, but there's a little line here that says, this medicine is an NSAID. Exactly how it works is not known. It may block certain substances by their linked to inflammation. And NSAIDs treat the symptoms of pain and inflammation. They do not treat the disease that causes these symptoms. So exactly how it works is not known. My friends, we do all this wonderful stuff, but we don't have a clue how things work or why. We're still grubbling around in the dark. We just change stuff up randomly and see what it does. We're still doing stuff by means of alchemy. Let's just mix some stuff together and see what we get. Chemistry is the same problem. This is the ethylene molecule, which is a hydrocarbon. And then by complete accident, somebody discovered by accident in 1938 by Roy Plunkett, figured out by accident they inadvertently swapped out the hydrogen molecules for fluorine molecules, and they invented one of the most remarkable materials by complete accident that we've ever discovered. This is ethylene. This is tetrafluoroethylene, 4-fluorine ethylene. This is also known as Teflon. Silly putty. They were looking for something and they had an accident, or they were changing stuff up randomly, and out came this material that was completely useless. They figured out, hey, we could sell it to kids as a toy. So that's a chemical mistake, a mistake of chemistry. Nuclear power. We know enough of the conditions under which radioactive materials decay to allow us to build bombs and power plants. However, we don't know why things decay. Just because we know that something does something doesn't mean we know why something does something. Okay, that modern fission reactors are only 2% efficient is evidence to me. This is called the poor efficiency tale. I forgot the number of the rule of acquisition for that. It's evidence to me that we really have no clue what we're doing. And if we can build these very powerful hydrogen bombs, well, how come there are no fusion reactors? If we believe the sun is a fusion power plant, how come we can't make a fusion power plant on the Earth? We really don't know what we're doing, folks. Okay, but again, we really don't have to know much about something to put it to great use. I mean, consider the car. How many of you out there drive a car? You can put a car to great use. But many of you don't understand anything about how an internal combustion engine works, nor do you have to. You don't have to understand how the battery works. You don't have to understand how the radiator works. You don't have to understand how the computer that controls all the functions of the car works. You don't have to know any of that stuff to put a car to good use. Same with your smartphone. It's a marvel of modern technology with computers and memory and all kinds of stuff, and you don't have to know anything about how that stuff works, but you can put it to great use. Okay, because monkey do does not mean monkey no. But unfortunately, people, because of our fabulous ability for utility, gives a lot of false impression out that we really understand what it is we're using when we don't. And this is basically what I just said before. So what we really need is a theory of everything, and then proof that we don't really know much. Okay, if we really had a theory of everything, this is how our world would change. We would have a cure for cancer and cure all known diseases, including aging. Or at the very least, we would know the causes of it. Okay, we'd have designer materials with magical properties that I could not even imagine right now. We would have faster than light starships with speeds expressed in kilowarps, thousands of times the speed of light. None of this bullshit in Star Trek, warp 5, we only go 5 times. Yeah, sure. That's going to be helpful. We'd have abundant, cheap, clean energy. We'd have 3D atomic printers, not powered by atoms. They would actually be printing at the atomic level. Able to replicate anything from raw matter, even garbage. It would make gold worthless. Because you could just go into a garbage dump, start printing up gold. The exodus of the earth would begin. We would start expanding to new worlds. Theoretical physicists will have to find new work. Nothing left to do. We've discovered everything. Essentially, all the predictions of Star Trek, except for the transporter and holodeck, would come true. And there's a lot of other predictions, including social changes. Okay, so to recap, the utility fallacy. We are still in the age of alchemy where we try different things to see what we get. I mean, what do you think a super collider is for? If we really knew what we were doing, we had a theory of everything, we would not need a super collider. Most of the technological marvels are due to trial and error development, empirical modeling, or just sheer accidents. Not because we have any carnal knowledge about how atoms or the universe works. Okay, so monkey do does not mean monkey no. That is rule of acquisition number 3, the utility fallacy. Thank you very much.